Dear students, in this video, we are going to discuss about identical cells. Identical cells means the cells having same EMF, same internal resistance. And now we will try to combine the identical cells. So first of all, we will be studying that what will happen if I have identical cells and I choose to group them in series combination, like series grouping of cells. So these are few cells that you can see in front of you. Okay, this cell is having EMF E, this cell is having EMF E, and so on. And what I've done, I have connected all these cells in a series combination and they are connected across the two ends of the resistor. Now the current will start flowing from the positive terminal of the cell to the negative terminal. Okay, and now we will be studying what will be the equivalent EMF. Do you remember that when you had unidentical cells having different EMFs, different internal resistances, then what used to be the equivalent EMF? Equivalent EMF used to be E1 plus E2 plus E3, which means equivalent EMF used to be the sum of individual EMFs of different cells. Okay, but here if we will use the same result, but here in place of E1, E2, E3, I'll simply write E plus E so on up to n terms, because I can suppose that there are n cells. So the equivalent EMF will be equal to NE. And what would be the value of equivalent internal resistance? Again the same thing. When I took unidentical cells, the equivalent resistance came out to be R1 plus R2 plus R3 plus R4 plus so on. Okay, now in place of R1, R2, R3, you can simply put R, because here you are simply having identical cells. Okay, so this will be R plus R plus R so on up to n terms, and it would be NR. So what would be the total resistance? Total resistance will be equal to the resistances, internal resistances of all the cells plus this external resistance that you have connected in this circuit, right? So after that, you need to see that current will be equal to, current flowing in the circuit will be equal to, we know that V is equals to IR. So I will be equal to V by R. Here in place of V, we have E equivalent, EMF equivalent. So that will be equal to E equivalent upon overall resistance. Now E equivalent is equal to NE. So I have written it. Overall resistance is equal to NR plus R. That also I have written. Now there are two cases which arise over here. Case number one, when this external resistance is much greater than NR. When this external resistance is much greater than all the internal resistances of all the cells taken together. Okay, then if R is greater than NR, much greater, then NR can be neglected in comparison to R, and current flowing will be equal to NE upon capital R. So this means this is equal to N into current flowing through each cell. Okay, so after that there is case number 2, and case number 2 says that if this R is much less than NR, then this R can be ignored in comparison to this NR. Okay, so now small NR will remain here and capital R can be ignored. So I will be equal to NE upon NR, and NN cancels. So you are left with E by R, by small r. Now E by small r, E is EMF of one cell and small r is the resistance of one cell. So in that case, E by R will be the current flowing through each cell. Okay, so what you can see, you can simply view this as when you want the current to be maximum, you know that the current is maximum here in this case. When you want the current to be maximum, you need to ensure that the cells or the battery that you are using has very, very, very less resistance in comparison to the external resistance that you are connecting. In that case, only the current flow will be maximum. In fact, I know that you must not have heard about internal resistance of a battery or of a cell till now. Like we have used batteries in the circuits of Ohm's law and so on. And what we knew that the current flowing was already very high. We never talked about the internal resistance of a battery, but let me tell you that a battery has an internal resistance, and that internal resistance can affect the flow of current. But if you want the battery to supply a good amount of current, then you must ensure that the cells that are there in the battery, that cells have internal resistance, but that internal resistance is very, very, very less in comparison to the external resistance that you are using. Okay, so that way we go for series grouping of cells. And now we will be discussing about parallel grouping of cells. Like you have cells and you have grouped them together in a parallel combination, right? So this is the cell. Of course, the cells that I am considering are identical cells, which means they all have same EMF and same internal resistance. And likewise, see, I am having them and I've connected them in a parallel combination, right? And this entire combo is connected to an external resistance thereafter. So after that, you need to find out the overall resistance of this circuit. Now you know that the resistances R and R, they are connected in a parallel combination, and that's why what will be the effective resistance in the parallel combination? It will be 1 upon Rp equals to 1 upon R plus 1 upon R, so on up to M terms if you have connected M cells, right? So when you'll add them, it will be M upon R, as simple as that. After that, Rp will be equal to R by M, right? And you can see that the effective resistance of all these cells is Rp. Now, can you figure out that this Rp and this capital R, they both are connected in a series combination, isn't it? Rp is the effective resistance of all these cells and R is some external resistance, and they both are connected in a series combination. So since they are connected in a series combination, what will be the effective resistance? It will be small rp plus R. Okay, so after that, we know that the EMF in a parallel combination is actually the EMF through each cell, isn't it? So current flowing will be equal to EMF through each cell divided by total resistance. Total resistance is R plus Rp. Here Rp has the value R upon M. This R remains as it is. Rp has a value R upon M. So I'll substitute the value over here. I'll solve it, and this is the value of current I'm going to get. Now I'll give you one task. You need to solve the special cases and you need to tell me what you have got. Special cases is case number 1. If capital R is much less than R upon M, then what is going to happen? Case number 2. If capital R is much greater than R upon M, then what is going to happen? Let me know. Solve these special cases. And after that, make a conclusion, derive a conclusion that if the cells are parallelly connected and you want to draw the maximum current, then how should you go about it? How should be the external resistance adjusted? Okay, so solve it and derive the conclusion out of it.